Hello everybody, thank you for joining today. My name is Venom and today we're going to be covering waves. So, some of our learning objectives include recall and understand the link between energy and waves, to define and use the terms frequency and wavelength, to be able to use the terms amplitude, period, wave velocity and wavefronts, and to be able to describe the differences between longitudinal and transverse waves with examples. So let's get right into it. Alright, so let's get started. Now straight away, I have here in the corner here, great physicists remember that waves transfer energy and information without, let's put in capitals, without transferring matter. Now that's a very key point that you need to remember. You need to remember that the wave is transferring energy and information, but it's not actually transferring any sort of physical objects. You can say it's not actually transferring physical stuff. It's transferring energy and information. That's something you need to remember straight away. So let's get into the anatomy of the wave. What pieces actually make up a wave? So I have a diagram here. Let's do it in different colors. So let's do the simplest one first. The wavelength. The wavelength here. So the wavelength is the distance between two, let's say distance between two identical points on a wave. Okay, so how can we find that on our actual wave diagram here? So if we look at this little piece here, where else on the wave is does the wave look exactly like this? That would be over here. So this distance here is our wavelength. Now the wavelength in physics is given a Greek symbol called lambda, which is sort of like an upside down y. So you can also write it like this. Either one is fine. I know some people find the little curls a bit difficult to do, so you can either use the top one or the bottom one. They both represent the same thing. So wavelength is lambda, and that is the distance between two identical points on a wave. Okay, so now let's have a look at amplitude. Now amplitude is the maximum displacement from the resting position of the wave, which is this red line here, the baseline you could say, and the maximum displacement. So amplitude is the maximum displacement. Now you'll notice that I'm saying displacement rather than distance. That's because we want the distance with a direction, so a vector. So we want displacement, the maximum displacement of a wave from its resting, which is this flat line here, resting position. So this right here is A for amplitude. Now let's write A there. Okay, so now we have our crest. What's our crest? So our crest is the point at which the wave is at max displacement. Now, you might be getting confused with, what's the difference between amplitude and crest though? Crest is only in the positive direction. We have our crest here, we have a crest here, we have a crest here. But you can also get amplitude in the negative direction. So if we had from here to here, that is also amplitude. If we had from here to here, that is also amplitude, but you can't call the lower point the crest. That is where the last one comes in, the trough. The lowest, well, I could say the, okay, well, we can call it the lowest point of the wave. Let's make this pen a bit thinner. The lowest point, or you could say maximum negative displacement of the wave, which we know is over here. So x, let's do an x. That is here. That is the control, and here that is the control. Okay, so now you understand the anatomy of a wave. Pause the video and try and get a blank sheet of paper and redraw this diagram here without looking at the video now. Now, let's start having a look at the differences between the longitudinal and transverse waves. Which one of these do you think is which? Now, most people know that the bottom one is the transverse wave, but for some of you, the top one, the longitudinal wave, may be new. So let's get right into that. Right, let's highlight them so we don't forget. Now, let's have a look at the anatomy of the longitudinal wave. We can see that it has areas where the waves are really bunched up here, and has areas where the waves are not so bunched up over here. So these areas have names. So where the waves are really bunched up, they're called compressions, obviously because the waves have been compressed. Compressions. And where the waves are spread out, you might see them be called expansions, but the word that we really use now is rarefaction. Rarefaction, which may seem really complicated, but the more you use it, the more you'll learn, and you'll learn to associate. Oh, when the waves are expanding, that's called a rarefaction, and when the waves are compressing, that's called a compression. So we understand that, and obviously let's label our transverse wave again here. So we have our wavelength from here to here, which is the distance between two identical points on a wave. And remember, I told you that that is given the symbol lambda. So now where can we find our wavelength on our longitudinal wave? Well, it's the same thing. Where there are two areas where the waves are exactly the same, so let's say rarefaction to rarefaction, okay, let's do it like that. That is a lambda, a wavelength. And where there are two compressions, let's say from here to, I'm going to go over my own writing, but okay, here to here, that's also a lambda. And in fact, with longitudinal waves, you don't really need to be able to label the amplitude, so that's only two things you have to worry about: where the compressions are, where the rarefactions are, and you need to remember that where there are two of the same, the distance between those two is the wavelength. Now let's start having a look at the definitions of longitudinal and transverse waves. Now there are two things that you need to remember when you're defining a wave: its direction of energy transfer and its oscillation. Now oscillation, that's a new word that I've just introduced, but it's fine, you'll understand it soon. An oscillation just talks about the cycle that a wave makes. So if a wave goes up, down, and then back up again, that's one oscillation. That's one cycle of a wave. Same way, if a wave expands, contracts, and then expands again, that's also one oscillation. That's one cycle of the wave. So how can we define a longitudinal wave? So a longitudinal wave is a wave in which the oscillation of the wave is parallel or in the same direction, as the energy transfer. Now let's break this down a bit. Now we talk about the oscillations of the wave. So in a longitudinal wave, it's if you do geography, you understand that longitudinal is around the Earth in the x direction. So if we have here, the wave is oscillating in the x direction horizontally, longitudinally, right? And also the energy transfer is happening from here to here. So the direction of energy transfer is also that way. So you can see that these two arrows are parallel, and so the direction of energy transfer is parallel to the oscillation of the wave. Therefore, this wave is longitudinal. Now, let's have a look at it in the transverse wave. So a transverse wave is a wave where the oscillations of the wave, let's write that a bit better, wave, are perpendicular to the direction of energy transfer. Now, again, let's break this down a bit. In our transverse wave here, we can see that the waves go up and they go down. But you can see that they're progressing this way. So the oscillations of the waves are up and down, but the energy transfer is left and right. So you can see that that forms a sort of, if I do, oh wait, sorry. If I do like that, if I do that, it forms a cross, which is perpendicular to each other. So therefore, this wave is transverse. Now, we also want to be able to state some examples about transverse waves and longitudinal waves. Let's start with transverse. One example of transverse waves are EM waves. So EM stands for electromagnetic, which covers the entire spectrum of waves that you need to learn about GCSE. So radio waves, X-rays, gamma waves, and also visible light all around us. These are all transverse waves. Another type of transverse wave is called an S wave. Now, S stands for secondary, and this is a type of seismic wave. So these are waves that travel through the Earth. Now, the way you remember an S wave is transverse is that transverse has an S in it, whereas longitudinal doesn't. So you remember that S waves are always transverse. So another example is water ripples. And this will often be demonstrated to you in a practical in your school. Now, some examples for longitudinal wave cover sound waves. Also, we get ultrasound, which is extremely high frequencies of sound. And also, we have another type of seismic wave, which is called P waves. The P standing for primary. So these are your examples for transverse and longitudinal waves. You do need to remember some of these, so pause the video and look away and see if you can state some examples for both transverse and longitudinal waves. If you can, you've now learned everything you need to know about transverse and longitudinal waves for your GCSE. Have a nice day.